Okay, in this podcast we're going to talk about the properties, acid-base properties of salts. And as you probably remember from Honors Chem, let me just get this working right. All right. An acid plus a base produces a salt and water. And all a salt is, it's a synonym for ionic compound. And an ionic compound comes from a cation plus an anion, right? Cation being positive, that's why it's a cat, and an anion being negative, right? Cations are metals, and anions are, they're metals or polyatomic ions that are positively charged, and the one we're familiar with is ammonium. Anions are either a nonmetal like chlorine or a polyatomic ion that is negatively charged, right? So ionic compounds are salts. So they're made from the reaction of acids and base. They are not always neutral, contrary to what you might believe. Some hydrolyze with water to make acidic or basic salts. So if you think about the water molecule, some of them will hydrolyze. Hydro means water, lyse means to split. They'll cause the water to split, and you can end up with an OH minus and an H plus. And if you have a cation, that cation can end up with the OH or with the H plus. Okay? So it's helpful in this unit to think about water as HOH, and when it splits, it's going to split like that and become this. Okay. So salts can be neutral, acid, or base. So let's take a look at how we decide. A neutral salt comes from a combination of a strong acid and a strong base. Okay, so that could be something like sodium hydroxide and hydrochloric acid, strong base, strong acid, and they will produce, of course, sodium chloride and water. So this would be a neutral salt. We can also get neutral salts if we have a weak acid and a weak base, but only if their Ka and Kb are equal. So you're not going to see many questions like this on the exam. You might see a question that says which of the following salts are neutral, and that's most likely you're going to find those that are made from strong acids and strong bases. Basic salts come from a combination of a weak acid and a strong base. The strong is going to dominate, and it's going to become basic salt. Acidic salts come from a combination of a strong acid and a weak base. So whatever is strong is going to dictate what you have in your salt. Okay, so let's talk about basic salts first. So basic salts come from, we said, a strong base and a weak acid. So this is an example of a basic salt. When we look at that, we can figure out what acid and what base produce this. So the sodium must have come from sodium hydroxide, which we know is a strong base. And the phosphate ion must have come from phosphoric acid, which we know is a weak acid. And because the base is strong and the acid is weak, we end up with a strong base. When we write this equation, what we want to do is, once we've identified that it comes from a strong base, we want to immediately on the product side show that we produce hydroxide ions. The lysis of water, the hydrolysis, produces the hydroxide ion, which is what makes it basic, and the H plus, so this comes apart as H plus and OH minus. The OH minus comes here, and the H plus comes with the anion. It goes in with the anion, becomes the weak acid. One of the things that's good to remember is to know and then remember is that when we write these hydrolysis reactions is that the anions or the salts, the parts of the salts that are strong, become the spectators. Okay? So in this case, the sodium hydroxide was strong, so the sodium becomes the spectator, and I don't include it in the net ionic equation. So all I include is the phosphate. So it's the phosphate ion with the water. It gives me hydroxide ion, and the hydrogens come over here with the phosphate ion and become phosphoric acid. Okay? Same thing here. I have calcium acetate. Calcium must have come from calcium hydroxide, which is a strong base, and acetic acid, which is a weak acid, so this is going to be a strong base. I immediately write that I produce the hydroxide ion, and what I have reacting with the acid then is, remember, the strongs become the spectators, so in this case the calcium drops off, and I'm left with the other ion, the acetate ion, and the acetate ion picks up the H+. The OH comes over here as part of the hydrolysis, and I end up with the weak acid, right? This plus this gives me this. Okay. Alright, so acidic salts come from, as you imagine, the opposite, strong acid and weak base. So if I think about something, a salt like ammonium chloride, the ammonium sounds a lot like ammonia, okay? So in this case, I have the chloride must come from HCl, strong acid, and the ammonium must come from the base, the weak base, ammonium hydroxide. Okay. Alright, so because we've identified it comes from a strong acid, we are always going to produce H+. Sometimes you might see this written as H3O+. It's going to come from the hydrolysis of water, right? We're going to have the H+ that comes this way, and we're going to have the OH- come this way. Now, this ends up becoming NH3. Okay? And let's take a look at this one. Might be a little bit easier to see. So we have aluminum nitrate. The aluminum must come from aluminum hydroxide, which is the weak base. The nitrate is part of nitric acid, which we know is a strong acid. So we know this is going to be an acidic salt. So we end up with H+ here, right? Because it's strong. The OH is going to, the hydrolysis is going to result in the hydroxide coming over to the aluminum, and the hydrogen ends up free in the solution, which makes it acidic, and I end up with the aluminum hydroxide. Okay? So in this case, the strongs become spectators, so here the nitrate is not involved in the reaction, right? It's the water over here. I'm in the H+, and I have the water, so I'm only going to be looking at the aluminum. Okay. So let's take a look. The other way you might get a question in an AP exam is you're given the Ka and Kb of an acid and a base, and you can qualitatively determine if your Ka, your acid dissociation constant, is greater than your Kb, your base dissociation constant, then the acid will dominate and your solution will be acidic. If my Kb, my base dissociation, is greater than my acid association, this will dominate and my solution will be basic, or my salt will be basic. And if my Ka and Kb are equal, my acid and base dissociate the same amount, and therefore my salt will be neutral. Alright, so here's our step-by-step. Step 1, we look at the acid and the base and ask which acid and which base must have formed it. Ask whether they are strong or weak. Strong wins, so if it's a strong base, it becomes a basic salt. If it's a strong acid, it becomes an acid salt. If we predict that it is a basic salt, we first write the OH on the product side. If we predict it's acidic, we write the H plus on the positive side. The strong becomes the spectator, and we can leave that off, the net ionic. Okay, and then we write water as HOH on the reactant side, and then we look at where the hydrogen and the oxygen or the hydroxide go. So let's take a look at one. Alright, so what is the qualitative pH of iron 3 nitrate? So first we're going to look at this and say which acid reacted. Well, nitrate must come from nitric acid, and iron must have come from iron hydroxide, right? So nitric, it's strong. Which base? Iron 3 hydroxide, it's weak. Therefore we have a strong win. So we have an acidic salt, right? So we write H plus being created from the HOH. Strong is also a spectator, okay? So we cross out, so the strong is the nitric, so we cross out the nitrate, right? Here we have the nitrate, we cross that out. And we're left with the iron plus 3 hydroxides, and they're going to, if we get it all balanced, we're going to make 3 hydrogens and iron 3 hydroxide. Okay, so we want to predict whether an aqueous solution is formed from these. That's acidic, basic, or neutral. Okay, so the first thing I'm going to do is identify where these came from. So it's NaOH, so that's a strong acid, a strong base, and must come from acetic acid. Okay, so therefore I have a basic salt, so I know that I'm going to produce hydroxides, and this is going to come from HOH. The strong is a spectator, so I'm not going to use the sodium, so it's going to be the acetate ion. The hydroxide came over here, so the H plus is going to come on this, and I'm going to end up with HC2H3O2. Not too bad, right? Alright, so ammonium nitrate, this must come from ammonium hydroxide, this must come from nitric acid. Because I have a strong acid and a weak base, I'm going to end up with an acidic salt. So I want to indicate that I end up with H plus. It comes from HOH. I know that the strong ion is a spectator, so I can cross that out. So I'm going to end up with the NH4 plus HOH. And this actually would produce NH4OH, but one of the things you need to know is that that immediately decomposes into NH3 and water. And because this is already in water, I don't need to show more water here. So I really end up with H plus NH3. Okay, this always immediately decomposes. Okay. And this is what you get. Okay. So let's take a look at this. I have aluminum, which must have come from aluminum hydroxide, which is a weak base. And SO4 must have come from the sulfuric acid, which is a strong acid. So this is going to be an acidic salt. I'm going to produce hydrogen ions. It's going to come from HOH. My strong is a spectator, so that comes out. And I start off with my aluminum plus 3, and the water is going to split, and I'm going to end up with the OH coming over here, so I'm going to end up with aluminum hydroxide. Okay. And I will need to balance this, so I'll need 3 of those and 3 of those. Alright, not so hard. Alright, so sometimes you'll be asked to determine the pH or pOH of an acidic or basic salt. So in order to do that, you have to first identify, is it acidic or basic, right? The hydrolysis reaction, just like we've been doing that. And then because it's going to be either it's going to come from a weak acid or base, we're going to have to use a Rice table to calculate H plus and OH to find the pH or the POH. So let's take a look at one. Alright, so we want to calculate the pH of 0.3 molar sodium fluoride. The Ka for HF is this. Okay, so let's take a look at this. Sodium must come from sodium hydroxide. My fluorine comes from HF. So I'm going to end up with a basic salt. Yet they gave me a Ka, and I really need a Kb to figure this out. So the first thing I can do is I can get a Kb because I know Kw is Ka times Kb. So Kb is going to be Kw over Ka. So that will be 1 times 10 to the minus 14 over 7.2 times 10 to the minus 4. So let's punch that. 1 second EE negative 14 divide by 7.2. Whoops. 7.2 second EE negative 4, and I get a Kb of 1. I'm just going to call it 1.39 times 10 to the minus 11. Okay. So now I can use a Rice table to figure out what my hydroxide concentration is. Alright, so my reaction, I'm producing base, right? So I'm producing OH minus. It's coming from water, which will not be part of the reaction. My strong is my spectator, so I have F minus plus water gives me OH plus HF. Okay, so that's my reaction, ICE. Initially, I have 0.3 molar of this. The water will not change, so I'm not going to include that in the reaction. It's a pure liquid. The hydroxide starts off as 0 and 0. My change is I lose X here, I gain X here. So this is 0.3 minus X. This is going to be X, and this will be X. So my Kb is going to be my OH concentration times my HF concentration over my F minus concentration. And if I punch those in, I'm going to have X for OH, X for HF, so that's X squared over my F concentration, which is 0.30 minus X. And that's going to be equal to my Kb, which is 1.39 times 10 to the minus 11. Now my Kb is tiny, 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 so looks like I can neglect my X, and you want to indicate that you've neglected it when you put that on the AP exam, so they know what you're doing. So I end up with X squared is equal to 1.39 times 10 to the minus 11. So I'm just going to take this and punch it over here. Enter times 0.3, and I end up with 4.167 times 10 to the minus 12 is X squared. X is going to be the square root of that, which is going to equal, I'm just going to do the second square root, pick that up, enter, enter, and I end up with 2.04 times 10 to the minus 6 is this is my hydroxide concentration, right? So to get my POH, it's going to be the negative of the log of that number, and that is going to be 5.69. So my pH is 14 minus my POH. So that's going to be 14 minus that number, and that will be 14 minus that POH, and that will come out to be 8.31. Let's check sig figs. I've got 2 sig figs, 2 sig figs, so I want 2 sig figs, which means 2 places after the decimal, and that is my answer. Okay, let's take a look at one more. Alright, so I want to calculate the pH of a 0.1 molar ammonium chloride solution, and the Kb for ammonia is 1.8 times 10 to the minus 5. Okay. Alright, so I have ammonium hydroxide is where this must have come from. I have HCl, so this is going to be an acidic salt. I'm given a Kb, so first thing again, I need to get my Ka. Ka is going to be my Kw over my Kb, which is 1 times 10 to the minus 14 over 1.8 times 10 to the minus 5. Let me clear that. 1.8 second. Did it wrong. 1.0 0.0 second EE negative 14 divide by 1.8 second EE minus 5 gives me 5.556. I'm just going to call it times 10 to the minus 11. That is my Ka. Okay? I'm going to write my equation. Because it is an acidic salt, I'm going to make H+. It's going to come from water. My strong is my spectator, so I'm going to use the ammonium here. And what we just said before was ammonium we make ammonium hydroxide, right? Which immediately decomposes to ammonia and water. And we already have water in the equation, so we're just going to put the ammonia here. Okay. Now I can use my Rice table. My initial concentration of my ammonia from my ammonium chloride is going to be 0.1. My initial concentration of H is 0 and 0. I'm going to lose X from here, gain X, 0.1 minus X, X, and X. So my Kb is going to be my H plus concentration times my NH3 concentration over my NH4 plus concentration, and that is going to be X and X, so that's X squared over 0.1 minus X, and that is my K equal to my Ka, which is 5.556 times 10 to the minus 11. Again, a tiny dissociation here, so I can neglect X. So I end up with 0.1 times this, which I'm just going to call 0.5556 times 10 to the minus 11 is equal to my X squared. So my X is the square root of 0.5556 times 10 to the minus 11. So my X, which is equal to my H plus concentration, is going to be, let me just multiply this here, times 0.1 equals, and then I'm going to take the let me see, did I write that wrong before? Was that 0.1? 5.55 times 10 to the minus 10. Yeah, that should have been 10. So that's 11. This is still 10. Okay, which is the same thing as this, right? So I'm going to take the square root of that second square root of that number, and I get 7.4 times 10 to the minus 6. Alright, so the pH of this is going to equal the negative of the log of this, which is going to equal negative log, pick it up, and I get 5.13. I want two sig figs, got two sig figs, 5.13 is my pH. Alright, so we're going to stop there.